Hey guys, it's Mr. Krieger. This is a review of the normal distribution in probability. So please print up the lesson. Okay, so this is the first question. Men's shirt sizes are determined by their neck sizes. Suppose that men's neck sizes are approximately normally distributed with a mean of 15.7 inches and a standard deviation of 0.7 inch. A retailer sells men's shirt in sizes small, medium, large, and extra large, where the shirt sizes are identified in the table below. So at 14 inches to less than 15 inches is small, from 15 inches to just less than 16 inches is medium, etc., right? Because the retailer only stocks the sizes listed above, what proportion of customers will find that their retailer does not carry any shirts in their sizes? Show your work. So I had already started to set this up. So this retailer sells shirts from size 14 neck size to size 18. So we basically need the area in between these two numbers using 15.7 as the mean. So what we need to do is we need to get our calculator and we need to go to the distributions and we're going to do normal CDF, and the lower value is 14, the upper value is 18. Standard deviation is 15.7, and the average is 15.7 and the standard deviation is 0.7. And that gets us 99.19%. So the area in here, I didn't represent it well, this is really much wider, is practically 99.2%, which means less than 1% of customers will fail to find a shirt in their size. Okay? That's how you would work that out. Okay, let's take a look at part B. Using a sketch of the normal curve like I did here, illustrate the proportion of men whose shirt sizes is medium. Calculate this proportion. So for part B, we want to make a new normal distribution with a mean of 15.7. And for medium, we want to go from 15 to 16. And we want to find the area inside there. Basically going to be doing the same thing. We're going to go to the normal CDF, the distribution normal CDF. This time we want to go from 15 to 16. Same mean, same standard deviation, and here we get 50.5072. So this is the proportion of men who need a medium size, okay? And part C, which I'll do over here, of 12 randomly selected customers, what's the probability that exactly 4 will request size M? Show your work. All right, so we need at least 4 that will request this size. So this is going to be a binomial PDF. I'm sorry, at least 4. I'm sorry, that's my mistake. Exactly 4. So this is going to be that binomial distribution. We're going to use the binomial CDF. And if we go into the calculator to check that out, into the distribution, binomial CDF, you're going to have to scroll down. This one's going to be a PDF because it's exactly 4. If you wanted, exactly 4. If you wanted a range, you do binomial CDF. But we're doing binomial PDF. We're picking 12 customers. That's the number of trials. The p-value, we got that from part B, 0.5072. And we want exactly 4. When we paste this, you're going to see what this looks like. It's going to be a 12, 0.5072, 4, and we get 0.1139. This is the probability, is about an 11% chance that 4 of the next 12 randomly selected customers will want a medium size. Okay, so that's how you do question number 1. Let's go take a look at question number 2. Okay. 9 sales representatives, 6 men and 3 women at a small company wanted to attend a national convention. There were only enough travel funds to send 3 people. The manager selected 3 people to attend and stated that the people were selected at random. The 3 people selected were women. There were concerns that no men were selected to attend the convention. Calculate the probability that randomly selecting 3 people from a group of 6 men and 3 women will result in selecting 3 women. Well, here's how we're going to do this. We say, well, the chance of picking the first person as a woman, since there's 3 women, the probability of picking a woman was 3 out of 9. Once we've selected a woman, then the chance of picking the next person being a woman, since there's only 2 women left, it would be 2 out of 8. And then the probability of picking the third person as being a woman, since there's only 1 woman left, would be 1 out of 7. If we multiply this out, we get 6 out of 504, which is 0.0119, about 1%, maybe slightly more than 1%. Okay, Part B says, based on your answer to Part A, is there a reason to doubt the manager's claim that the 3 people were selected at random? Explain. If we were to do a hypothesis test and got a probability so low, the null hypothesis would have been, men were reasonably expected to be on a trip, that we would have rejected the null. It's not reasonable to expect that the 3 women were selected just by random at such a low percentage. Now, it's certainly possible, but very, very unlikely. So I would say yes. Only approximately 1.2% chance that this happens. If we were to do a hypothesis test at an alpha level of 5%, then we would clearly be rejecting the null. It seems likely that these women weren't selected by chance, but more likely that they were selected purposely. Okay, and Part C says an alternative to calculating the exact probability is to conduct a simulation to estimate the probability. A proposed simulation process is described below. Each trial in the simulation consists of rolling 3 fair 6-sided dice, 1 die for each of the convention attendees. For each die, rolling a 1, 2, 3, or 4 represents selecting a man. Rolling a 5 or 6 represents selecting a woman. After 1,000 trials, the number of times the dice indicate selecting 3 women is recorded. Now it asks, does this proposed process correctly simulate the random selection of 3 women from a group of 9 people consisting of 6 men and 3 women? Well, if you look at the probability we selected here, the probability changed each time. The probability of selecting the second woman wasn't the same as the probability of selecting the first woman. These events were not independent of each other. But the simulation that's being conducted, each die is the probability of getting a man or a woman stays the same each time. So in essence, they're doing in the simulation probability with replacement, and we did in our actual probability count probability without replacement. We're going to get different answers. So we would say no, this will not simulate the true probability since the real event involves dependent probability, but the simulation involves independent events. I would say here instead of probability, I put events. Okay? All right, so that was problem number 2. Let's take a look at the last problem. Okay. An airline claims that there's a 10% or 0.10 probability that a coach class ticket holder who flies frequently will be upgraded to first class on any flight. This outcome is independent from flight to flight. Sam is a frequent flyer who always purchases coach class tickets. A. What's the probability that Sam's first upgrade will occur after his third flight? Now, this is something we haven't practiced in our review, and that is that part A is a geometric probabilities problem. If you remember what that is, a geometric probability is one in which we say, what's the probability that the first flight that he gets upgraded on is the fourth flight? So remember, if we were to do that, and I'm going to go grab just another sheet of paper just so you can see. When we did that, we would do something like, okay, so the chance of him not getting an upgrade on the first flight is 0.9. The chance of him not getting an upgrade on the second flight is 0.9. The chance of him not getting an upgrade on the third flight is 0.9. And finally, on the fourth flight, it's 0.1, or essentially 0.9 to the third times 0.1. This was a geometric probability problem, okay? That was the one I just described was a very simple one. This is a little bit more complicated. What's the probability that Sam's first upgrade will occur after the third flight? So what I would do is I would find the probability that it happens on the first flight, the probability that it happens on the second flight, the probability that it happens on the third flight, and then 1 minus this sum will be the probability that it occurs after the third flight. So the probability that his upgrade occurs on the first flight is 0.1. The probability that his upgrade occurs on the second flight is 0.9 times 0.1, or 0.09. The probability that it occurs on his third flight is 0.9 times 0.9 times 0.1, or otherwise 0.9 squared times 0.1, which is 0.081. We're going to take the sum of these, 0.1 plus 0.09 plus 0.081, which is equal to 0.271. This is the probability that his first upgrade occurs on the first or second or third flight. The probability that it occurs after this is going to be, so I'm going to write this. So the probability of the upgrade, the first upgrade, occurring after the third flight is 1 minus the 0.271, which is 0.729. Okay, that's part A. Part B. What's the probability that Sam will be upgraded exactly 2 of his next 20 flights? Now, this is a different kind of probability. This is a binomial probability because they're specifying the number of flights he's going to take. There's a fixed number of flights, as opposed to when will the first upgrade occur. That could occur after the 7th flight, 15th flight, 100th flight. There's no stopping this from continuing. Here, we're going to look at 20 flights, and we want to see what the probability of him being upgraded exactly 2 times out of that 20. That's a binomial PDF situation because we're doing exactly 2. We're not doing greater than 2 or less than 2 or something. So that would be a CDF. This is going to be a PDF. The way we're going to put this in our calculator, we're going to go to the distribution binomial PDF. The number of trials, we're looking at 20 flights. The probability that he gets upgraded is 0.1. We're looking for exactly 2 out of those 20 flights being upgrades. So when we do this, we're going to be putting 20, 0.1, 2, and that gives us a probability of 0.2852. So there's a 28% chance that this will occur. 2 out of 20 flights will be upgrades, okay? Part C. Sam will take 104 flights next year. Would you be surprised if Sam receives more than 20 upgrades to first class during the year? Okay, so we want to see the probability he gets more than 20 flights. Well, this is going to be a binomial CDF situation, but if you recall from class, I told you binomial CDF counts from 0 up to a value, not from a value up to the total. So we're going to have to do a 1 minus. So what we're going to do is 1 minus binomial CDF. Again, we're counting a whole range of values, not sticking at a specific number. A whole range of values. So there's 104 total flights in the year. The chance that it gets upgraded is 0.1. And what we want to do is this probability, not with the 1 minus, this probability is the probability of him getting between 1 and 20 flights upgraded. 1 minus this is the probability of him getting 21 or more flights upgraded, because this is more than 20 flights. So that's this whole thing means 21 or more upgraded flights. And again, this one will be a binomial CDF. So I'm going to put the 1 minus in, and you will go to the distribution, and I like to scroll up because it goes to the binomial functions quicker. Binomial CDF, we're talking about 104 trials, p-value is 0.1, and we're putting in 20, and that's going to give us 0.001. So this is 0.001. Now, the question, though we found the probability of that, which is far less than 1%, right? And it says, is this reasonable? Would we be surprised? Yes, we would be very surprised. This is a very, very unlikely outcome. Again, if we were to do a hypothesis test using an alpha value of 5%, we would reject the null. This is a very, very rare outcome, so we would say with such a small probability, this is not a likely outcome, and we would in fact be surprised and use context if he was upgraded on 21 flights or more. Okay, so anyway, you have a few homework problems to do, so please try those out.